Welcome back to ChemDoctor, and this is the second video in the series on chemical kinetics. And what we're going to do in this video is calculate the average rates of the reactants and the products in a chemical reaction given the time versus concentration data for a reactant. So in the left side of the screen here, what I'm showing is the time and concentration data for the conversion of N2O5 into nitrogen dioxide and oxygen. And this is a typical set of data that you're going to find offered in a university level general chemistry course or advanced placement or even a high school level class. If we were to look at how this data is graphs, and I'll do a quick graph here by freehand. It'll be represented this way, where the concentration of N2O5 is on the vertical axis, and the time, which in this case is in seconds, will be on the horizontal. So in a way of thinking here, to bring this down to some familiarity, the x-axis is the time and the y-axis is the concentration. Remember that the square brackets means molarity, and I think I'll label that here so that it's clear. So the square brackets is molarity anytime we see them, and that's regardless of whether it's kinetics or equilibrium. So square brackets is molarity. All right, so if we look at how this graphs, we can see that the data with the N2O5 starts at 1 molar, and over the course of a reaction, usually that's going to result in a curved line that's going to go down like that, and it'll be asymptotic somewhere down here depending on where the equilibrium position for this reaction is. In other words, the curve may not terminate at 0. It may terminate at a value that's going to be higher than that. The main thing is, in kinetics, we're studying usually the initial rate of the reaction, so that means we're going to be in somewhere close to 0. Now, in this reaction, what we're doing is we're going to calculate the average rate for the conversion of N2O5 into the other components in the chemical reaction. And specifically, we're going to look at 4 total data points. We're going to look at one at 200 seconds. We're going to look at one at 400 seconds. We're going to look at one at 600. And then we're going to take one final point that's going to be out here at 1400. So we could visualize this way. So we're going to look at a point here on the graph. We're going to look at a point in this region, an average rate here and an average rate here. Now remember in the first video what I said about this. So in essence, what we're doing is taking a tangent to the line, which is going to be in this region, this one, and this one. So there's going to be an XY value for each of these points, and what we're going to be doing is finding the average rate at each one of these points, and the average rate that we find at each of these points is the average rate of that time interval and not anywhere else. And we'll see that as we go ahead through and do these calculations. So let's go ahead and start, and the first interval that we're going to do, and we'll write the average rate this way for N2O5. So we're going to use a negative sign in front of the delta symbol here, because the concentration of N2O5 is going to decrease with time because it is a reactant, and the reactant is going to be going away while the products will be formed. That's why this curve over here has the shape that it does. It goes down like this and then approaches the base of this graph, which is approximately 0 here. So we use a negative sign to indicate that, and I'll put our time interval in, which is going to be from 0 to 200. Whoops, 0 to 200. All right. Now, this is going to be equal to then, now remember, we're essentially looking at the slope of a tangent, and the slope function here is going to be y2 minus y1 over x2 minus x1. All right, that gives us the slope of a line. So we're looking at the time interval here from essentially from 0 to 200. So that means this is going to be 0.88 minus 1 over 200 minus 0. And the value that we get here will be, and I'll put my minus sign back just to indicate again that we're looking at the disappearance of the product. So this is the rate, and the units will be in molarity per second. All right. Again, the negative sign indicating that we're following a reactant which is decreasing with time. All right. So this would be the average rate for this interval here, which is occurring between essentially 0 and 200. Now, the next interval I want to look at is the one between 200 and 400. So we write the expression essentially the same way. All right. Now the interval here will be 200 to 400. All right, and that's going to be equal to 0.78 minus 0.88, and that will be divided by 400 seconds minus 200 seconds. All right, and the rate that we're going to get, again, I'm going to put my negative sign in to indicate we're following the disappearance of a reactant, and we see that the rate is 0.0005, and that's molarity per second. Now, you can see an important issue here, all right, because if we compare this rate between 200 and 400 seconds versus the one between 0 and 200, you see clearly that it's decreasing. And again, that's the point of the negative sign here, is to indicate, again, this is a reactant, it's disappearing with time, and we're producing products. All right, now if we look at the next interval, and this one we're going to go between 400 and 600. So we write again the same expression, and the interval will be, let's see, 400 to 600. And in this case, we're going to, the numerator will be 0.69 minus 0.78. And that's molarity, and the interval here will be 600 seconds minus 400 seconds. So you can see the denominator in each case is the delta T is 200, and this will be 0.000, and the rate is 45, and that again is molarities per second. And we see that again the rate is decreasing, it's doing what it's supposed to be doing. And the final interval that we're going to look at, and I did this one just to get this point that's further out in the curvature of this transition, and so that we would see a more dramatic decrease in the rate. So this will be delta N2O5, just like the other expressions, over delta T. And we're going on this one from 1200 to 1400, and it will equal 0.43 minus 0.48, and that will be over 1400 minus 1200, and it gives us another data point here, which will be 0.00025, and that's again molarity per second. And again, you see the rate has decreased again. So starting at the beginning down to this final point, we see that the rate has decreased, which it should for a reactant. Now, what I want to do really quick is show the viewer how we find the average rates of the other two components that are part of this reaction. So we're producing NO2 and we're producing O2. We found the average rate at 4 different time intervals for the N2O5. So how do we find, let's look at this first time interval that's going from 0 to 200, all right, seconds. How do we find the other two components? So let's find the NO2 first. So how do we find this? All right, so what we're going to do is we're going to use stoichiometry to solve that problem. And what I'm going to do is use the average rate of the N2O5 that we discovered for the time interval from 0 to 200. So I'm going to write that down here, and it'll be 0. I'm going to drop the negative sign now because now we're finding for a product, and it is being formed rather than disappearing. So we're going to drop the negative sign to indicate that this is a rate of appearance versus one of disappearance. And to use the stoichiometry, what I'm going to do is write down, I'm going to put a label on this. I'm going to call it what it is. It's N2O5. And this is the average rate for N2O5 at this time interval here. Now, to get the average rate of the NO2, what I'm going to do is use a ratio from the balanced equation. This is just like a regular theoretical yield stoichiometry problem. So in the numerator, there are going to be 4 NO2s because it is for every 2 moles of N2O5 that disappears, we're going to form 4 NO2s. So in the denominator, we're going to have 2 N2O5. And so the average rate of NO2 at this time interval is going to equal 0.0012, and that will be molarity per second. And you can see the difference between the 0.006 and the 0.0012 is literally twice. In other words, 4 divided by 2 is 2. 2 times 0.0006 gives us 0.0012. So this is the average rate of NO2, and I'm going to go ahead and put the label here so it's clear what we're talking about. So this is the average rate NO2 during the same time interval. And we can use the same technique to find the oxygen. So it's going to be 0.0006 molarity per second for the N2O5, and then we're going to use stoichiometry. There's 1 mole of O2 produced for every 2 moles of N2O5 that goes away. So the average rate of production of the oxygen is going to be 0.0003 molarity per second, and I'll label it O2. So this is the average rate O2 for the time interval from 0 to 200 seconds. And this guy here was the time interval 0 to 200 seconds. Okay, and with that I'm going to go ahead and close.